Hello and welcome to Seismic Data Processing course. Today we have the main processing, the common midpoint sorting, and velocity analysis. So what is the gathering? In seismic exploration, we record thousands of individual seismic traces. And to process and analyze this data effectively, we group these traces based on shared characteristics. This collections of grouped traces is called gathering. So we have thousands of individual traces. We gather them in order to have one data. So the five basic types of gathers we have: common short gather, common receiver, common offset, common midpoint gather, and common depth point gather. In the common short, there's one source and multiple receiver. There's the near receiver and far receiver. Within the common receiver, the second type, we have multiple source and only one receiver. We have common offset. This we have multiple source and multiple receiver. And common midpoint, this we have the midpoint in here. We have the source and receiver, and we have its goal is collected within one point in the interface. We have common depth point, where the reflected is collected from one depth point in here. So the difference between the CMP and the normal and the flat reflections, the CMP, the common midpoint and common depth point, will be the same because one collected depth from here. But if you have dipping, the common midpoint will start working wrong. We will have multiple reflections from here, multiple reflections, and will overlap to each other. And also what within the depth point, the dipping reflections, if you have the dipping in here, so the common depth point, it will have multiple reflections representing from one depth point. How does the gathering or processing work? The process of creating gathers is called sorting, and it moves the data between different domains. So these are the domains. We have first data. This is the short domain. We are collecting the data in the field, and the processing in here involve like reformatting, resampling, geometry. And then we move to the CMD common midpoint domain. In this domain we do some process like the deconvolution. We remove the multiples elimination, velocity analysis, and then we move to the offset domain. This is where we are do the stacking to stack all the data from multiple traces to one trace. And also we have the stack domain process. This is after the stack. We convert the data to 2D or 3D modeling, and also we do the intercept grade involved. So we have also advanced and special gathers. So this is advanced technique for the gathering type. This is common azimuth gather. These gather are created by grouping traces with a constant offset but varying azimuth. So we have one collecting points, but you have different azimuth. Different azimuth, that means you have different depth of angles. So from 0 to 360 degrees, the azimuth is depend on the degrees. So we'll have different type of degrees would collect from one point, one depth point. This is the azimuth gathering. The unfold convergence, we have the fold. For a given subset of receivers, the maximum number of time a CVAD is hit by waves is called the fold convergence, and is computed by this equation. So this is the short gathering, and we have the receiver, and we have the CMD and the fold, and maximum recording. So the fold is depend on the C number of channels and the peaking interval, receiver ground intervals, and the source interval. What is the velocity analysis? So we have to differentiate between the speed and velocity. The speed is the distance traveled per second, but the velocity is distance traveled per second in a specific direction. So in here, the velocity difference per speed by you adding the direction, then to the right, to the left, to the mid. So why does this matter? Because when the sound wave travel to the ground, we have to calculate calculate the velocity and the time, and also the direction for these waves going down, then back and up. So our world, we always talk about velocity. So we have multiple methods for seismic velocity analysis, but the velocity analysis is the process of finding the correct seismic velocity for each subsurface layers. So we have to find the velocity for each subsurface layers, and that will help us to convert reflections time to depth. And this is to improve the seismic imaging. So this is done by interactive on a processing workstation using combination display like semblance plot, gathers, and velocity spectra. So this is done by the software. So the key point in here is just it is one of the most time consuming steps. This is the most important step, velocity analysis. Interpretation must be particularly based on evolving judgment, not just software, and repeated several times during the processing to refine result. Velocity picking is an art, so meaning it's based on a scale and experience, not just numbers. So they have type of velocity. This is interval velocity, average velocity, RMS velocity, and NMO velocity. This is stacking velocity. The interval velocity is the velocity between two reflections. We have the average velocity, the total distance for all the layers, and divided by the time, the average time for all the layers. We have the RMS velocity, that's the root mean square velocity. So this is identifying to collecting the velocity for the second layer multiplied by the time, and then dividing by the velocity for the first layer and dividing by the time, and then we take the root mean square for this velocity to calculate the mean root velocity. Also we have a stacking velocity, that's when you have horizontal reflections, and then we have the dipping in here, so I calculate how much the difference between the horizontal, the interface, and the dipping reflections. So more accurate ways of estimating velocity was driven by Hewitt-Dix in 1955. This takes into account the actual path travels and velocity calculated by using the actual path. So this is the square root mean square velocity. You calculate the v2 multiplied by the time. This is one-way travel time, and then velocity for the first layer multiplied by the first one-way travel time, and then this is the average of the travel time, and then we take the root mean square for v to get the VRMS. And this is the velocity with the density. So different type of rocks, we have different type of velocity and density. These for example, we have the sandstone here, we have like 2.6, starting from 2.6, and then you have the 2 gram per centimeter density, and then the limestone we have the, for example, 2 above the 2.4 density, and we have 6 in here for the velocity. So increasing the velocity with kilometer per second, and then we have the dolomite velocity in hydrite is higher in velocity, and the shell, the low velocity and high density. And this is how the VMRS work. You take the root mean square and you get the VRMS. So this is all you need to know within this lecture. So thank you for watching, and see you in the next video.